Alright, hey everyone, we're back and with the next and final segment of our thermodynamics video um, playlist. And so in this segment, we'll begin by solving problems involving certain thermodynamic processes or state changes of the gas, for example, like adiabatic processes, isochoric, isobaric, isothermal, etc. So this problem is taken out of the Tsoko's book, and it's example question number 5 in chapter 10, uh, pardon me, 3.4, which is also it's also higher level material. And over here, if you see these equations that I've listed will help us in solving this question. So the question reads, a monoatomic gas is kept at constant pressure 3 times 10 to the 6 pascals, initial volume 0.1 meter cubes, and temperature 300 Kelvin, which is constant. Pardon me. The pressure is kept constant. The initial volume is 0.1 meter cubed, and the temperature is 300 Kelvin. If the gas is compressed at constant pressure down to a volume of 0.8 meter cubed, find A. the work done on the gas, and B. the thermal energy taken out of the gas. So it's the A part is quite simple. Since we know that work is equal to P delta V for an isobaric process, we can simply plug in the numbers. It's important to keep significant digits in mind here. Excuse me. So now that we obtained that's A part, and you might have noted that although the change in volume is negative, now B part. So B part for B part we'll need to utilize the first law. Delta U, change in internal energy, is equal to Q minus W, and thus to find the thermal energy taken out, we must find the change in internal energy of the gas. Now we'll utilize the above equation and put delta in front of PV. So delta PV plus work, which is this. Like the formula states, 3/2. And that ultimately leaves us with, by plugging the numbers, that leaves us with negative 1.5 times 10 to the 5th joules. Now, to finish off this segment, I'd like to talk a bit about the second law of thermodynamics and a bit about entropy. Now, first of all, let's just erase this and it'll make it simpler. Now, where are we at? Alright, okay. So now, basically, the second law of thermodynamics. The second law of thermodynamics implies that well, first of all, there's many versions of the second law of thermodynamics. There are also many processes in thermodynamics that are consistent with the first law, but are basically impossible. That's why the second law comes in. For example, the spontaneous, or that is without the action of another like outside agent, transfer of thermal energy from a cold body to a hotter body is actually possible through the first law, but in reality it is impossible. Another example would be the air in a room suddenly occupying just one half of the room and leaving the other half empty is actually possible according to the first law, but once again, not according to practical knowledge and the second law. Finally, a glass of water at room temperature suddenly freezing, causing the temperature of the room to rise. Such concepts are consistent with the first law, but in reality they're impossible and need a second law to basically illustrate them and define them. So out of the many versions of the second law, the one we've chosen to discuss today is Cassius's law, which states that no heat pump can transfer thermal energy from a low temperature reservoir to a high temperature reservoir without work being done on it. In other words, you can't have a reaction spontaneously occur in which heat travels from the cold reservoir to the hot reservoir. Instead, you need to have work done on that system. And a very common diagram that's normally used with that is this one, illustrating the different reservoirs. Let's use red. So this side of the system would be the hot temperature side, and we would have the system connected. And there would be a heat engine in between. Which is thus connected to the cold side. And then this would be the cold temperature reservoir. Now, in this system, for the heat to flow this way, oops, sorry, for the heat to flow this way, from the cold to the hot, there would need to be work input into there would need to be work input into this heat engine. And this work would be equal to, whether there's these values, the heat on the low side and the heat on the high side. These values this work would be equal to QH minus QL. And since we know that the heat involved on the hot side is obviously greater than the heat involved on the low temperature side, this work will always be positive. Now another way to state this second law of thermodynamics is in terms of entropy. Now with entropy, what we usually do pardon me. Right. With entropy, what we usually do is so basically the second law of thermodynamics through entropy states that in a natural process there is an increase in the system in the system's entropies, or as it is stated otherwise, we can also say, pardon me, 1 second. There we go. So this is this law as well, this part of the law as well can be stated in many ways. One of the representations is can be shown like this: GS, which is the symbol for entropy, S is the symbol for entropy, is equal to DQ over dt, pardon me, over T, sorry, over T. And now you're probably thinking, what's this new entropy thing he's talking about? Well, actually, entropy is a quantity that's associated with the disorder of a system, or the randomness of the particles that are involved in the system. And now you're probably starting to get an idea that as the temperature of the particles increase, or as the particles change phase from liquid to gas or from solid to liquid, its entropy increases as it goes from a phase with lesser intermolecular forces to phases like from a phase with greater intermolecular forces, such as solid, to a phase with less intermolecular forces, like a liquid or gas. The entropy and the disorder, randomness of the particles' movement would increase. And basically, overall, the like I said, The second law also states that overall the entropy S of the universe is increasing since all natural thermodynamic processes, for example, chemical reactions, certain thermodynamic operations, transfer of matter and energy, etc., all increase the entropy of the universe. Now you're probably thinking, whoa, we learned about conservation of energy, conservation of momentum. Why isn't this new entropy thing conserved? Well, this is because in all processes, the overall randomness of the system is increased. For example, even in a freezing process, though the entropy of the substance decreases, the flow of heat, or Q fusion, into the surroundings, there's a flow of heat into the surroundings, which thereby increases the entropy of the surroundings and thus the overall entropy of the entire reaction. You guys should research this a bit on your own, and do a few problems on the stuff that we've covered. I know this is a lot to cover in a few videos, but hope you enjoyed it. And that's all from Smith's Fizz. Hope to catch you guys later. Thanks for being such a great audience.